So let's start today's class. We are going to learn about the 8086 and bus cycles and how to do loop delay calculations. So essentially there are three types of bus cycles. These three terminologies are used. One is known as instruction cycle, then we have something known as machine cycle, and then we have something known as T states. Okay. What is a machine cycle? Machine cycle is essentially four separate instructions. Like the first is the fetch instruction, then decode, execute, and store. So these four separate steps together is known as a machine cycle. So whereas in the earlier days, when the primitive microprocessors, each instruction could be completed with these four steps like fetch, decode, execute, and then store. But in an advanced microprocessor like 8086, an instruction cycle is pretty complex. So it could have more than one machine cycle. So machine cycle is a very basic cycle. Like it could be like reading an information from the memory. So you fetch the data from the memory, decode it, execute it, and store it. So the read operation from the memory is a one machine cycle. Similarly, writing some data into the memory is one machine cycle, right? So writing some data into the input output port is an one machine cycle, whereas an instruction cycle, we will see that it could be complex. It could be more than one machine cycles. So this is what a machine cycle is. Instruction cycle is it's a complex instruction which we write in 8086. So it could be it could contain more than one machine cycles. So that is why so we'll see some examples of instruction cycle, so that will be very clear how complex it is, and it can contain up to from 1 to 4 machine cycles, right? We'll see that. And then there is something known, this is known as the T cycle. T cycle is nothing but the number of clock pulses that are required to complete an instruction. So this is the most important thing for calculation of an actual time taken for doing an instruction. So each instruction we should know what is the amount of clock cycle. So if we know the clock frequency, we can in turn compute the total time taken for an instruction. So among these three, this is what will help us in calculating the actual delay and time taken for each instruction. So machine cycles can be again classified into an opcode fetch, memory read, memory write, input output read cycle, and input output write cycle, and all of them takes 4 clock cycles. Okay. So what is an opcode fetch is nothing like when we write a program, it is it is stored into the memory locations, right? So 8086 first what it does is the IP counter is pointed towards that memory location, and that code is going to be fetched and decoded and kept in the queue. All right. So there is a pipeline structure. So that operation of bringing the code which is written in the memory into the bus control interface unit, and it is brought into the BIU and it is decoded. So that process is known as opcode fetch. Okay. So I think this is the slide for it. So what it does, how is it done is first you place the memory address, right, into the bus bars from A0 to A13 during the first clock. So it is similar to the memory read operation which we learned earlier. So we place the address bar. So this address is taken from the IP register, and then the ALE goes high, so that this whatever is the address is latched, so that the same bus bar can be used for data transfer also. So you have the ALE line going high for some time in the first clock, right? In the next clock, when negative edge of the clock, right, what happens is the read signal goes low, right? So that we are going to read the data now. So for a certain duration, since after the read signal goes low, the data line here, because data is the data line is only from 0 to A7 and A0 to A15. Whereas the other data lines is not shown here, so address lines. So in fact, I think this slide is from 8085, but as for 8086, you will have in the initial things all 0 to A20 lines, and in which that data will be placed, the address will be placed. Now when the data line, when the read signal goes low, so the data will be placed on the from the memory, it will be placed onto the data lines. And then in the third cycle we skip that third cycle, and in the fourth cycle we allow the data to be read into the microprocessor. Okay, so it takes total of 4 cycles. So even let me go back to the memory read operation of 8086. Again this I'm sorry for this I think this slide of 8086 is shown here because the address lines is only 0 to 16. Yeah, I think it is the full address lines are shown here. So the address lines will be initially for the first clock, the address line will, for a memory read operation, the address lines will be energized, and the address to which from where the data needs to be brought is placed on this address lines. Also you will have the BHE bar information also required, because you to select which is the chip, right. So you require along with the address lines, you require the BHE dash signal also, and then we have the address latch enable signal also coming high. So this will enable this address latch enable will enable us to latch on the data of the address and the BHE. Okay. So in the next clock cycle, again if you see here it's shown in the positive edge of the clock cycles, the data is being. So in the next positive edge of the clock cycle, okay, the read cycle, the read is enabled. So after a certain duration, the data from the memory will be available onto the data bus bar, right. So and then you have the read in the next clock cycle, you don't do anything, and in the fourth clock cycle the data is fed into the into the microprocessor, right. So similarly you have input output write operations, which is very similar to the memory write operation. The only difference is the instead of memory signal, memory input out stroke IO bar signal going high in the case of memory read write operations, in the IO write operation this signal will go low, because so this will enable the signals to be diverted to an input output device rather than the memory. So because the same, it is again the same address lines and the same data lines for memory or for the IO line. So the only difference which comes here is memory stroke IO line, okay, that going low, right. So that is why otherwise everything is same out here. So input output read operation, again here the only difference between IO read and the memory is here that the memory stroke IO signal goes low in this case, whereas in the memory operations the signal will go high. So these are the various kinds of operations. Now this is something probably important for your exam also, something known as instruction cycle. Okay, so the instruction cycle consists of two different things. One is known as the fetch cycle, the other is known as the execute cycle. Okay, so in the fetch cycle what is done is the IP will point towards the memory, okay, and from the memory the data is whatever is the code that we have written that is brought into the bus interface unit. It is going to be that data is going to be fetched. Okay, so since it is an 16-bit processor and the data lines are 16, from two memories the data will be brought simultaneously into the BIO. Every time 2 bytes of information will be fetched. After fetching that, the instruction is decoded, and if there is a requirement of if the instruction could be register to register, so that then both the registers will be kept ready for the an arithmetic operation or logical operation in the execute cycle. Or if the data is to one of the operand is a memory, then the address line, physical address line will be generated and kept. Okay, only that much is done in the fetch cycle. Okay, so I'll just repeat what is done in the fetch cycle. Two instructions from the memory location, 2 bytes of instruction is fetched, right. it is decoded. Okay, once it is decoded, and if it is, if there is a memory element involved in the instruction which is to be done, then the physical address is calculated and kept ready. Okay, in the execute cycle, the actual instruction is is executed. If there is a data to be brought from the memory, then that also has to be brought. Okay, if it is only pure register operation, then it will be straight away will be executed without any delay. Whereas if it is if there is a memory element involved in it, then the data from the memory will be fetched in the execute cycle, and then it will be and then the operation will be carried out. Okay, so the difference here, till the physical address generation will be done here, the data will be fetched from the physical address. Okay, so in earlier processors, now this entire duration was important, whereas now in 8086, since it's a pipelined architecture, this will happen even before. This is going to, like, one instruction is being executed, then the next instruction fetch cycle is already will be done in the background, right, by the bus interface unit. So the actual time for an instruction will be only the execute cycle, because this will be done prior to the execute cycle parallelly by the processor. Okay, that is known as pipelining, or this is going to save the time. So the fetch cycle is actually not very important in 8086, because only the execution time is important. But nevertheless, we will learn how to compute the total instruction cycle also. So now there are certain rules to identify the number of machine cycles in an instruction. Okay, if you have if the addressing mode is direct, immediate or implicit, then number of machine cycles is equal to the number of words. Like suppose I write an instruction increment AX. Okay, so in a memory location, it will occupy only one byte of information, right? So in the this is the code. This code is ultimately going to be saved into some memory location. And what is the time taken to fetch this instruction is, now it is going to be taken only one machine cycle, because it is going to get this data. This is only 1 byte information, so it will just take now one machine cycle to get it and decode it. Okay, once it is decoded, so there is no need of generation of any physical address, because it is a register operation, right? So it will just get. So similarly, this is also push F. Okay, again it's an 1 byte opcode, so it is going to take one machine cycle. Pop AX is again an 1 byte and 1 byte instruction, so it is going to take another only one machine cycle. Now you have move AX BX. Okay, this is again one word operation. So since it's an our processor 8086 has got one word data can be transferred from the memory, because it has got 16 data lines. So this also will take one machine cycle. This is an instruction which is going to take this is move AX, and then we have given an memory address here, specified the memory address. So this is going to take, and this has got 3 bytes of information. So it is going to take 2 machine cycles to get this information into the BIO. Okay. So if you see, these are all direct addressing. So there is, so once it takes once it brings this data 2001, the physical address will be adjusted, it will be generated and kept ready for the next execution operation, because 2001 is a direct physical address. Okay, it just has to calculate the physical address and keep it ready for the execution cycle. So here, but however, since it is there are 3 bytes, it will take 2 machine cycles out here, right? But in case the addressing mode is indirect, then there will be, you will have to add one more machine cycle to decode that indirect addressing mode to generate a physical address. For example, I write move AX and within square bracket BX. So this requires only one machine cycle to get the data. It is in a single byte of this is 2 bytes, so it will take in a single machine cycle. This data is brought into the BIO, but then I am not interested in BX, right? I have to generate the physical address corresponding to BX. so I'll require one more machine cycle here, right? So that one more, the decode operation is going to take one more, so the fetch cycle now becomes 2. So whenever there is an indirect addressing, so you will have to first see the opcode length, and if it is whatever is the opcode number of words, those many machine cycles, plus you will have to add one to cater for the decoding of the indirect addressing and generate the physical address. So it will take actually 2 machine cycles. Is this clear to all of you?
So could you please explain the move AX, comma BX and move AX, comma 2001H part again? I
Okay.
mean, how does it take one clock cycle?
Okay,
Yeah.
this is only one byte of information. So we just have to when we place when we are going to read this from the memory. So this is 40x will be brought into the BIU, right, and it will be decoded. So there is so it is a register operation. So you don't have to generate any physical address also. So it is just gets over in one machine cycle. Push F is also 1 byte of information. This is also brought into it is not one clock cycle, it is one machine cycle. Okay, so each machine cycle could take up to 4. So this is going to if you see move AX, it is going to take an more it consists of one memory read operation. So there will be 4 clock cycles. That is different. We are talking about machine cycles here. Okay, we are not talking about clock cycles. So this is one machine cycle is it's a total read operation. If I go back here, uh, uh, this is fetch the information, decode it, execute it, and store it, right? These 4 operations together is called a machine cycle. So here we are talking about machine cycles here in this example. Okay, so this data will be read, okay, into the BIU from the memory. It will be decoded and it will be kept ready for the next operation. It will be stored into the final storage will be into a temporary register of 8086, and then when the execution cycle happens, this instruction from the temporary register will be it's already decoded, now it will be executed. Similarly, push F and pop F, these are all 1 byte of information, so code. So we will be getting it in within one machine cycle. Within one machine cycle we will be able to get that data, decode it, and store the information in the temporary register, so that in the execution cycle it will just be executed. So move AX BX is also, it is an 8 byte and 2 byte information. So it will also be, it is possible to get it in, because this is in 16-bit data. So it will be brought in one read operation, and then decoded it, and then it will be executed. So in the decoding in 2 temporary registers, data of in the temporary registers, data of AX and BX will be there, and then it will be in the execution cycle, it will be whatever the data will be transferred from BX to AX. Similarly, move AX within square bracket. In this case, if you see, there are 3 bytes of information, so it cannot be brought in a single machine cycle, because two read operations are involved here, right? If you see, because in a single read operation you can maximum get up to 16 bits, so 2 cycles will be required out here in this case, right? And then 2001 is the actual address of the memory. It is direct addressing. So the physical address will be in the decoding part, the physical address will be generated and kept ready. Okay, so in the execution cycle, from that memory it will be brought into the AX. Okay, now in the indirect addressing mode, if you see, we write move AX BX. So this requires only this is on an 16-bit opcode. So 16-bit can be transferred in a single machine cycle. So this will be transferred into the into the BIU, one of the registers. You have 6 registers, right, in the Q part also. So this will be brought there, and then but then the data available in out here, okay, is BX. Okay, that is not that cannot be directly used for generating the physical address, right? That cannot be placed as an address line. So you have to generate that physical line address. Okay, so now you have to get that data which is available in the BX data to and then generate the physical address. So it will take one more machine cycle to generate the physical address. Is it okay? Is it clear? So whenever you have indirect addressing, you will require one more machine cycle to generate a direct physical address. Okay, is it okay?
Sir, so basically we need to see the number of words in the given opcode and then
Yeah,
decide how many machine cycles it will take. So
correct.
if there are more than one word of data, then it will take two machine cycles. Is that right?
Yeah, correct.
Yes, sir.
Okay,
Understood.
it could go like if this is only an example, but there could be more than two machine cycles also. You can have a lengthy opcode also where you have extra like bx plus si and offset of a word also. So okay, those kind of instructions are also there. And if it is an indirect addressing, you need to add one more address machine cycle there. Okay, that is also important. Okay. Now the instruction cycle. You don't have to really remember these things. Okay, I'll share a PDF with you. So 8086, the manual. This is gives the clock cycles for each instructions. Okay. So for each of the instructions, how many clock cycles? This is in the execution part. Okay, this is not in the opcode fetch. During the execution, AX BX to move this data, how many clocks are required? Add AX BX, how many clocks are required? Right? We saw for the read write operations and all, it took 4 clock cycles, but for move operations and add operations, only 2 clocks are required, because during the opcode and a fetch instruction, these registers are kept ready. Now we just have to do these operation. So the number of clock cycles is required only 2 here. Multiplication is a complex thing, so you require a large number of the clock cycles. Move beyond some immediate data, if you have to, it requires 4. Like compare AX, so it requires 9 plus some more cycles to get the data from the effective address. Okay, so the value of EA is also given towards the end of this chart. So jump not 0. Okay, this is going to take excuse me, if it's going to jump, then it is going to take 16 clock cycles. If it is not going to jump and come out of the loop, then it will take 4 clock cycles. Similarly, loop, if it is going to go and execute a loop, then it is going to take 17 cycles, clock cycles, and if it is going to come out of the loop label, then 5. So these are the clock cycles. So I'll share a PDF also. You don't have to remember this. For each of the instruction, how many clock cycles are required. Okay, so and now this is some example. Yeah,
Hello.
tell me.
So in the previous slide, when you showed move AX comma BX,
Yeah.
so that is basically I think it's basically a 2 byte instruction. So it will take 1 clock cycle for decoding, right?
No, 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 no. See, this is instruction cycle, execute cycle. This is already done. This part is already done. We are only talking about the execute cycle here.
So do we add the number of fetch cycles plus the number of execution cycles?
In earlier processors that was the case, but in 8086 we don't do that. We just see about, because this is done parallelly, right? We learnt about pipelining in 8086 where the data will be see, there are 2 different things we are studying here. Okay, one is the total machine cycle required for an instruction. Okay, this is the example which I gave, and then and this is telling only about the fetch cycle. Okay, fetch cycle. Okay, this is this part. Okay, this part, and then execute cycle. Okay, in the execute cycle, I'll give you some more examples of how to do the execute cycles in machine. So this is in the execute cycle, it is talking about the clock. Okay, this is not talking about the machine cycles. Again, it is talking about the clock. Okay, this is a number of clock cycles within the execute, right? Is it okay?
Yeah, yes, sir.
Okay. Now we'll now come back to the machine cycle thing. So if you see move AX BX, how many machine cycles will it take? Okay, now we are talking about the total time taken for the instruction. Initially we talked only about the fetch cycle. Now we are talking about the this instruction, we are talking about the total time taken for this instruction, total machine cycle for the instruction. So if you see, it will take an one to fetch this opcode, it will take an one machine cycle, which is an essentially opcode fetch is nothing but memory read operation, right? We are reading something from the memory, so it will take only one machine cycle. And then for the execution, we don't require a machine cycle here, right, because it is just both the registers are kept ready. So the moment execution cycle comes, it will directly be executed, this operation will be executed. So there will be no machine cycle. Okay, there will be some clocks, or two clocks are required to do this operation, that is different. Okay, we are talking about in terms of machine cycle. So there is no machine cycle involved in the execution part. Is it okay? So there is only opcode and a fetch. The fetch cycle is available here in move AX BX register, because both are registers here. So there is no memory read write operations in the execution cycle. So the total machine cycle for this, for the total instruction cycle, machine cycles in the instruction will be only one. Is it okay? I will give a few more examples, then it will become even clear. Okay, so now we are talking about this operation where we are adding BX with this memory content. So if you see, this is the opcode, so there are two words. So we require an opcode requires two machine cycles, opcode fetch, right? And the execution part in the machine cycle, in the machine cycle we need to there were two machine cycles are required for opcode. To execute the instruction, again we need to get this data, only the physical address has been generated in the opcode. Now you need to read that data from that memory location. So one more machine cycle is required in the execution part. So the total machine cycles required is 3 machine cycles. Is it okay now? In the last example, since it was only register operation, there was no requirement of again getting some data, there was no read cycle involved. So there was no machine cycle involved in the execution part. Whereas in this case, since there is an memory data requires to be obtained from the address from the memory, there is one more machine cycle required, that is an read data. So the total number of machine cycles is 3 in this case. Is it okay?
Sir, I understood the opcode fetch part, but I understand how one machine cycle would execute the instruction.
In the execution part, okay, what has happened in the opcode fetch? We have got this data out here, right? We have got this data from the memory location, and we have decoded it, and decoded it means we have generated the physical address, right? Now to execute this instruction, right, if you have to execute this instruction, this data which is available in 0100 needs to be brought into a temporary register of the ALU for it to add, right? So that fetching of the data will take one machine cycle. It's an read operation, right? 4 clock cycles read operation. So that is why you will have one more machine cycle in the execution part. Is it clear now?
So, but after we fetch the value stored in the offset address,
Yeah.
we should also add, right? So will that also take another extra cycle? It will take two clock cycles to add, shown in that PDF, in that image.
Uh, no. You're talking about this PDF, this chart?
Yes, sir.
No, just okay. Time being, I should have put this later on. This is clock cycles. Okay, just no, forget about this. Okay, so this is 2 clock cycles. This doesn't constitute an machine cycle. Okay, so for moving this, for computing these things, it doesn't take a machine cycle. Okay, so this doesn't require a machine cycle, complete machine cycle out here.
Is there any sort of relationship between a machine cycle and a clock cycle?
No, machine cycle consists of 4 different operations. Actually, this will be like a machine cycle means it has to be a read cycle, read from input output, or decoding. So the machine cycle consists of 4 different steps, and reading, decoding, like we saw this out here, right? Yeah, these 4 instructions have to be there in a machine cycle. Okay,
Yes, sir.
fetch, decode, execute, and store, right? So this table is only the clock cycles required for execution of these commands. So don't confuse it with the machine cycle out here, right? So like for move AX BX, okay, let me again cover it once more. For move AX BX, okay, to fetch this data, okay, opcode fetch, you require one machine cycle, because this is only one word in code. So you will take one machine cycle to fetch this data, whereas to execute it we don't require any machine cycle, because the data is, so during the opcode fetch, this in the temporary data AX and BX will be there, will be directly available. So the moment execution is to be done in a 1 or 2 clock cycles, it will just give the results. So there is no need of fetching any more data anywhere. So data is readily available for the execution to happen, right? Whereas in this case, right, this add bx, so it require, this code itself is of 2 words, so it will take 2 machine cycles to get the data out here, right? So 2 machine cycles are required, because there it is a 2 word length opcode, right? Once it is, then it will on the opcode fetch, we have seen that the physical address will be generated. Here we are talking now, it is not only register operation, it is a memory operation. So when we are executing it, now whatever is the physical address data available, we are not going to add that, we are going to get the data from the memory. Then some data is to be fetched from the memory, so it is going to take one more machine cycle, which is known as the read data from this memory location. So one more memory cycle, machine cycle will be used during execution, and once that data is read, it will just add these 2 data. Okay, so the total machine cycles will be 3 in this case. Okay, now we have one more instruction where add. Now the destination register is a memory location. Now if you see, this is the opcode for it, it is it is 2 word length. So you to fetch, you will require 2 machine cycles to get the opcode, because it is word length is 2 out here, right? To execute the instruction, so first we need to read the data which is available in this memory. So we need to get that data and put it into a temporary register. So that will be taken 1 machine cycle, and then it will, once it is brought, it will be executed. After, it will just take 1 or 2 clock cycles to execute it, and once that is done, you need to, again you require one more machine cycle to store the result back into this memory location. So this is a memory read operation, this is a memory write operation. So if you see, the total machine cycles required in this case is 4. Is it clear now?
Sir, so yeah, I think the number of machine cycles depend on the number of memory operations. Like
Yeah,
memory
it
read.
depends on the memory operations essentially.
So if any, if there's only any register operations, then we don't consider them part of the machine cycle.
Yeah,
Is that
if
right?
it is pure register operation, we don't consider it as a machine cycle operation.
Yes, sir.
Right. Only thing is, only thing is, when we are fetching the data here in the opcode, right? If the address is not direct, then then we need to add 1, okay, to generate that physical address also for indirect addressing. That is the only. Otherwise, machine cycle you can vaguely call it as memory read write operation or input output operations. Okay, how many, you can just compute the number of memory read operations, memory write, input output read, and input output. Only difference would come here when in an indirect addressing, apart from read write operations, you will have to add, if it is an indirect mode of operation, then you need to add one more machine cycle to generate the physical address. Is that okay?
Yes, sir.
Okay. Now execution. This is again convert byte into word. This is the opcode is just 98, so it will take just one memory, one machine cycle. Okay. Now these are the delay loops which I explained yesterday in the lab also. So once we have a motor, if you want to slow down the speed of the motor, right, we can introduce these kind of loops. There I used a different commands here, so so the way computation method is going to be the same. So how to insert delays, when there is some instructions. So this is how we can insert certain delays. So if you see move cx 100, right, so the move cx is going to take 4 cycles. Okay, now we are not talking about the opcode fetch and machine cycles, we are talking about T cycles. Okay, so actually this machine cycles and all is not really important as far as 8086 is concerned. Okay, 8086, if I more important is this clock cycles. So this is available in the 8086 manual, so I'll share this PDF with you. Okay, I'll put it in the download section within the lecture folder. So these are the actual clock cycles which are taken. So if you see, if I go in 8086, okay, you don't have to consider this fetch cycle because it happens in parallel. So we are only concerned about the execute cycle, and within execute cycle also we will not now talk in terms of machine cycle, but we will talk in terms of number of clocks required to execute this, right. So this is given the number of clock cycles for execution. Okay, so because with this only we can find out what is the actual time taken for executing the cycle, right. So okay, so if move cx is 4 cycles, and then loop here, right, it is 17 cycles to go back to the loop, right, to loop it here, and come out of the loop is 5 cycles, right. So it is what it's going to do every time when it counters loop here, it is going to decrease the value of cx, and then if it is not a 0, it is going to again insert the same here itself, it is going to loop in the same place. So it will insert a delay, then only then the next instruction will be taken. Once it comes out of the loop, only the next instruction will be executed. So you are inserting a delay here. So how to compute the delay? So total number of clock cycles which will be required here is 4 for move cx 100, 100 into 17. Okay, because you have put a value of 100 into cx, so 100 into 17. Okay, minus 12. Now, why do we put this minus 12 is for the last cycle it is coming out of the loop, right. The total is 17, whereas 5 is the clock cycles required to come out of the loop. So 17 minus 5 is 12. So this is the formula which is used. Okay, so you have 1692 cycles, and now if it's a 5 megahertz clock, then it will be 1 by 500, which will be 1 by 5, it will be 200 nanoseconds, whereas if you are using a 12 megahertz clock, it will be 0.083 microseconds. So this is the time taken for time period for a clock. So you have to multiply these two, and you can get it the exact time delay which will be introduced by this instruction, right. So many a times you might be given to calculate, if the time period is mentioned, then you will be told to calculate the value of n out here in this instruction to insert. Say if I want 1 millisecond delay, what should be the value of n? So you can put it in this formula, right, the value of n, and then get this will be 1 millisecond. So once you know the frequency, and if you know the total time, you will compute the total number of clock cycles. Once the clock cycle is known, then using this formula, the value, instead of 100 you put a value of n, and you get the number of value which is to be stored into the counter. Okay, so this is how the delays are introduced into the whenever we do practical circuits, there will be a requirement of putting these kind of delays, whether it is a motor, or if you are going to read some inputs from somewhere, right. So suppose you want to read some data from a temperature sensor, so you don't have to keep reading it and every now and then. So you can insert some delays and read it only at an interval of say 1 minute or so. So these kind of things can be these enables these kind of instructions enable us to insert delays. Okay. This is again one more example. Here we are moving a count into the CX register. Here we are putting an instruction NOP, that means no operation. So when we write no operations, and it skips 3 clock cycles. Okay, it doesn't do any arithmetic or logical operations. Whenever we write NOP, the microprocessor skips 3 cycles, right, and then we write loop here. So it goes out here. So in this case, what happens is you can get larger delays because now the formula for calculating the delay will be 3 plus 17 into n, right, because a factor of 3 also will come because it is going to skip 3 clock cycles here. We are going to do loop from here to the no operation, again come back to loop. So 17 is the clock cycles required for looping from here to here, whereas 3 is the clock cycle for the no operation command which we have inserted here. So microprocessor is going to skip 3 clock cycles out here. So this is the formula. The formula gets modified by 17 plus 3, and then you have to put this minus 12 because finally you are going to in the last cycle you are going to come out of the loop. So the difference, because it is going to come out of the loop, it requires only 5 clock cycles. So that is the reason you put a minus 12 there. So we can calculate the time delay accordingly now. So once you so in this case time delay is, if it is 1 millisecond time delay is required, then the value of n has been computed here, right. Again again you have to remember, it is not that this 0.083 is not sacrosanct. It depends on the frequency which we are using. Okay, so 0.083 has come for 12 megahertz clock cycle, right. For generally for LC86 we use a 5 megahertz clock cycle, so this will become 200 nano. So you have to be careful with that, don't mug up this data available 0.083. So this is also dependent on the frequency. So this is how we calculate the value of n. Okay, this value will come in decimal. So whatever is to be loaded into CX register in hexadecimal, it's shown out here, right. So if this value is put, it will calculate, it will create a delay of 1 millisecond. Okay, so is this delay loops and understood how it is done?
Yes, sir.
Okay. Then there are a few more things which we need to understand. This is something known as memory access time. Okay. So if you see, once we place an address by the 8086, okay, once the clock cycle goes low, there is some time taken for the address to be placed onto the bus bar. Okay, so till the bus bar, if you see from here, TCLAV, it stands for time from clock to address valid. Okay, so this is the clock which is starting here. Okay, and this is the TCLAV. So this is the clock which is coming here. So there is going to be some time, definite time required for the address to become stable onto the bus bar. So that is known as the so before that, if you try to compute the address, okay, there could be some errors because the data, the moment the clock is gone, the microprocessor starts putting the address data onto the address bar. So it is going to take some finite time for the address to get stabilized. Okay, so that time is known as the TCLAV, that is time taken from clock to address valid, right. So generally it is 110 nanoseconds for 5 megahertz clock. For 5 megahertz clock, so this is the time 110 nanosecond. So if you see the memory access time is the time taken. It is a specification of the memory which we are going to connect. So that means within 600 nanoseconds, the total time from, if you see the read operation is actually of 600 nanoseconds, but this time you have to cater additionally. So the memory should be the memory time should not be 600, it should be 600 minus 110, because this much time will get wasted, right. So the memory access time should be 600 minus 110, because this much time is going to be get wasted in the address getting stabilized. Okay, so the memory access time, it is 4 read cycles, which is in 600 actually. For 5 megahertz, it is each cycle is going to be 20 nano seconds. So the memory can be read in the third clock cycle, right? The fourth clock cycle, actually the next data is again pushed. So if you see the first clock cycle, the address changes. Second address cycle, the data is placed by the memory, and in the third clock cycle, the data is captured by the 8086. So if you see 3 clock cycles stands for 600 nanoseconds, right? So in the 600 nanoseconds is the total time which is generally required to capture the memory from the time the clock goes low. But since the address is going to be delayed by say 110 nanoseconds, so you have to write 600 minus 110 is the memory access time, right? Now there is also, once the memory once the read signal goes low, okay, the time taken, then the memory will be written out here onto the data will be from the memory will be written onto the data bus bar. But there is something known as a setup time, right? Before the microprocessor is able to read the information, the data should be stabilized, okay, before a few nanoseconds itself, right? Otherwise, if this is the cycle at which the data is going to be captured by the microprocessors, you can't have data changing just prior to that 1 or 2 nanoseconds before. So that is known as the setup time of a flip flop or any for this for setup time of the microprocessor. So this data requires to be stabilized beforehand itself. Okay, you can't have a data changing just before it is being read. So you will have this data to be written by the memory few nanoseconds before the data capture time. Okay, so that is known as T time data valid to clock. Okay, that is before the clock, 30 seconds before itself, the data has to be placed into the data bus by the memory. So that is known as TDVCL. Okay, so the total access time of the memory, you will have to delete these two second time taken also. So for only 460 nanoseconds is available for the memory to place the data. So once the clock goes low, okay, 110 seconds will be consumed by the microprocessor to put the address valid or put a valid address, and then the microprocessor will have to, before the completion of the third cycle, 30 seconds before itself, it has to place the data onto the data bus bar. So the total time available for the memory access is only 460 nanosecond, right? In case you are putting an slow memory device, okay, which cannot put this data within 460 nanoseconds, then we learned in our previous class that we can insert TW, right? So each TW will insert 200 nanoseconds for a 5 megahertz signal. So if you have a memory which is slower than 460 nanoseconds memory access time, then we can insert TW, okay, each clock cycle. So each clock cycle, if you are going to insert one TW, then it is going to insert 200 nanoseconds, then it will become 600 nanoseconds will be the total memory access time. So this is for a slower memory. So if you have still slower memory, you can insert one more TW, 2 TWs, then it will become 400 plus 460, 860 nanoseconds. So this is about memory access time. Is it clear to all of you?
So why do we add another clock cycle? I mean, what is the purpose of it?
If the memory, see, we saw this is the restriction which comes. This is the memory is given only this much time, and from the clock cycle, okay, from the start of the read clock cycle, for the memory to put the data within 460 nanoseconds, the memory has to put the data onto the data bus bar, right? But if it's a slow operating memory, right, then this much time, see, each memory device may not work as fast as we require, right? So there will be slow memory operating devices also. So in case it's a slow operating device, then we need to insert these clocks, right? Extra clocks, so as to cater for those slow operation of the memory. Is it understood?
So basically, we're inserting extra clock cycles to wait for the slower memory to finish the operation so
Yeah,
that it will sync
yeah,
in the end.
yeah, yeah, correct. Okay. So that's all for today. In next class, and we'll continue with the memory organization of 8086 in the next class. Okay, thanks a lot.